experimental model identification of vibroacoustic cavities with a calibrated acoustic source. In my presentation, we will see an introduction to the constructive aspects of the cavity, analytical and numerical solution, Dobson method, AFP method, experimental procedures, results, and conclusion. The introduction. My identification is in the low frequency band and the middle frequency band. The middle frequency band because it's the beginning of the frequencies of the voice, and the low frequency band concentrates in the cases of motor, sound of the motor passing through the car and the booming noise. We start with a simple experiment, a cavity that is a box, and we intend to make it in a car or in another cavity. The calibrated source, it's because here, like you can see, we didn't use the signal that goes out of the source. We use the signal that's measured. Use the signal that's measured that goes into the box. Exactly here. We put a source here, go the sound through this tube, and go into the box, and we measure what sound is going into the box. The constructive aspects, our box have 50 centimeters of width, 8 centimeters of length, 32.6 centimeters of height, 2.5 centimeters of thickness. The glass window have 30 per 20 centimeters, and the hole is 50.8 millimeters of diameter. This hole is where we pass cables and we put the source. Well, the analytical and numerical solution. The analytical is obtained by the wave equation, where we do some separations of variable and Fourier transform, and we can obtain the mode shapes and the natural frequencies. The numerical solution, we use it ANSYS 12. The harmonic responses, we use 200 substeps to a frequency band of 20 to 1000 Hz, and a frequency step of 4.9 Hz. The excitation was applied in a single point corresponding to the center of the orifice. We try to make it more like the experiment. You know that experiment is an area, but here with this simplification, it worked great. The Dobson method. What's happened? In the Dobson method, it consists in making a delta of receptance. We take the peak, where's the frequency in the peak, and making deltas of reference receptance in the frequencies around the peak. With this, we have making a linear regression and have a family of lines. This family of lines have the many linear factors, and with these linear factors we can make another linear regression and obtain model parameters like the natural frequencies and model constants. The rational fractional polynomial method, that is not in the article, it's a work that I do later, and it consists in reformulating receptors into polynomial functions. We define a wave function, minimize it, and then we decompose this polynomial function in rational fractions. The poles will be directly related to the damped and the natural frequencies, and the reals will be directly related to the model constants. This method is a multimode method in the domain of frequency. This one is a mode-by-mode method. It's in the domain of frequency too. The experimental procedures. We did the experiment in Brazil, humidity of 50% and temperature of 24 degrees Celsius. The excitation we used sweep logarithmic sine in a broadband of 100 to 3000 Hz. Time 1.5 seconds that the sweep made this frequency, and amplification of 2.5 dBp. Why we choose this time? Because with this time we can the signal that the lab will get is periodic, so our results we have greater coherence. The filters on one view, we use low pass filter 100 Hz because of the broadband, and high pass filter 2000 Hz. Why 2000 Hz? Because above 1500 Hz, we have a high model density, so we can see what's happened after that. So we stop here 2000 because to have a space to see what's happening. The data acquisition that's occurring on view. We have a frequency step of 0.5 Hz, and it's because of the high model density with a lower resolution. We can see what's happening. We need a higher resolution to have a good coherence and a good FRF. We start with a grid of 9 points, but our results are not great, so we divided it again in 49 points, and so we have a great result. The microphone amplification used in this Nexus BNP is inside 360 millivolts Pascal and outside 10 millivolts Pascal. What's happened? We put a switch sign program in this HP source, pass the excitate the source exit the speaker, and the speaker sends the sound through the tube, inside the box, and here the microphone is measuring what's going into the box. Another microphone is inside the box, and the holder by this hole. And the brew will amplify the sign of the two microphones, pass through the exit setup, pass to the lab view and the MATLAB, where it treats the data. What we did in MATLAB, we search for peaks. I program an algorithm that search for peaks on the FRF, and with the search for peaks, he applies the Dobson method and the FRP method. What happens in the Dobson method? Dobson method is a mode-by-mode method, so it's needed to know where's the peaks. And the FRP method needs to know where's the peaks because to have a good fit on the FRF that the FRP method makes, we need to increase the degrees of liberty of the method. And with that, he shows us more natural frequencies that really exist. So what we did, we have these natural frequencies of the FP and the natural frequencies that we searching the peaks, and we compare the two and have the real resonating frequencies. This is the results. Here's an FRF, like I told you. Here above 1000 Hz is high model density, and we can see what is happening. But we can see that we have some coherence here. The coherence is greater until 1000 Hz. Like you can see, we have 80 natural frequencies until 600. So above this, we have too much more, and they start coupling with one with another, and we can see what is happening. We can see that the biggest error was 1.1% comparing the analytical, the numerical, and the experimental solution. And in the major cases, the experimental is lower than the numerical and analytical. That shows because of the damp that reduces the resonate frequency. So we consider our experiment great. This is the mode shapes. These mode shapes are not in the article. That's the FP method. This is the mode 1. The mode 1 we can see, we can really compare with the numerical and the experimental one. We can see here the effect of the glass, the effect of the window of glass, and the next modes we can really see what is the effect. This is the mode 2, where we can really see the effect of the window of glass, creating a zone of lower pressure, and it's really compares with the numerical solution. The mode 3, exactly the same, the glass of window, giving interference of high pressure zone now, but it's really compared zones of high frequencies and zones of low frequencies, really compared. The Dobson method is not too good because it's a mode by mode method, and so it's a little bit less precise than the FP method. The conclusion, the natural frequencies are very close to the numerical and analytical ones, and the mode shapes that in the article we just show the Dobson method are not good. We consider this not good. Besides that, it seems like, but it's not good. This one is great. So the mode shapes now are good. And our next objectives is to say cavity plus flexible plate and cavity plus plate plus cavity. We start with this cavity plus flexible plate yet, but we just put the flexible plate above the box, and with this configuration, the flexible plate work like a damper. So the peaks are too smooth. All of them are smooth. So we can see the natural flux with this configuration. We are trying to fix it. Perhaps we're going to put cavity plate plus cavity, but measuring in the same case of the same source, in the same box where the source goes. And that's this. Thank you for your attention.
Okay, thank you very much. We have also time for questions. So are there any questions?
Did you use just one microphone?
Yeah, I use 2 microphones. Yeah, because in university places we don't have too much money to put 49 microphones inside the box, but it's the case that, I don't know, in this figure we can see. But we put 1 microphone outside and 1 microphone inside, and measure and open the box, put a microphone in the other microphone, measure, put the box, another point, 49 times. And with this, it's a little hard work because we put some mass above the box to reduce the dump and give more rigidness, give the more higher the box. So it's like take the weight and open the box and measure the microphone. It's a little bit hard, but it works.
I don't know if I understand, but do you include the window effect in your numerical analysis?
No. In my numerical analysis, it's just like a rigid box. We don't include the effect of this window of glass. What's happening here is because this box is already made on UNB. It's a box that was installed in Germany, here in Santa Catarina, and in USP. So we just use this box that's already there.
Any more questions?
So you have two measuring once. So how do you manage the phase in this kind of? You use always the phase related to this microphone.
The phase, I didn't look for the phase. What happened in the phase, but what I think, because it sounded I consider that it occurred almost at the same time. It's because it's periodic, so the sign of, I understand what you asking. Is that the sound goes in the box and the sound that passes here is not the same that's going there. But the time itself, I think that's too little that didn't interfere in my results.
And the other point you measure in the middle of the box.
Yeah. I forgot to talk. I measure right in this line, the middle line of the box. I try to measure in this way, but the results are not good because the source, the way preparing this box.
Maybe just a last comment you mentioned about the flexible plate. You didn't have any good result because of the dam.
The dam, because
you may try to improve the stiffness of this plate to try to avoid this high coupling in it.
Yeah, it's higher because we have a little borracha here.
Rubber.
A little rubber here. And this make the plate make the depth of the plate.
So any more questions, comments? No? Okay, so thank you very much. Yeah. This is the end of the session, but I think in about 15 minutes the other room.